Okay, so first thing I wanted to do for those of you who are either missing, Monday or Tuesday of this week, April 19th or April 20th of 2021, or just in general for those of you guys who wanted to see this again. This is what we did in class, right? So we're going to go over a couple of these problems on assignment 1. I like assignment 1, number 1, because the picture that is right here, this wooden block oscillating or moving back and forth on a table, based on a spring, is a really good analogy for what we've already talked about in terms of pendulums. So I'm actually going to start with a pendulum example really quick, and from there we will actually progress into or go back to what we had been talking about. So a pendulum, normally when a pendulum is swinging back and forth, we had a conversion of stored potential energy, which we would have described here as being at a maximum value, and no kinetic energy, right? Kind of like a child on a swing set, right? If I pull my kid back on a swing set to whatever height she's going to start at, I will just let go of her. She's not at the age where I'm going to start pushing her, so I'm just going to let go of her, let gravity do its thing, and let her start swinging. Well, as she swings from the upward position where I let go of her to this bottom position, and this is what we talked about back in Unit 9, all of that potential energy is converted into kinetic energy. That stored potential energy based on her height above her lowest possible position is converted into kinetic energy and is therefore converted into velocity. However, she doesn't like hit a wall, right? I don't have the swing set up so that she runs right into a tree and comes to a stop. She still has that velocity at this lowest possible position, and her momentum, which we also talked about, will carry her through all the way to the other possible end of this particular motion, right? She's going to go up just about as far as she had started in terms of height, and then turn around, come to a stop, turn around, and come back the other way. And that's how a swing set has always worked. This is how the pendulum in your pendulum lab had worked, right? So your potential energy on this other side reaches its maximum, right? We could calculate it, but we're not going to. The idea is that you have a lot of potential energy and all of your kinetic energy runs out because your velocity gets back to zero. Where am I going with this? Follow me. Here we go. We can do the exact same sort of thing. That cut out way too much. We can do the exact same sort of thing, analyze this in the exact same sort of way. Oh, there's no in between? Okay, that's great. If we take a look at not just potential and kinetic energy like we did in Unit 9, but if we start looking at forces, accelerations, and velocity like number 1 is asking us to do. I'm going to start here at the middle. This position we have always referred to as equilibrium, right there at the middle. That is the position that the swing would be on if it's not windy out and no one's swinging on the swing and it's not going anywhere. It's just its natural base position. It's the same position on your pendulum lab that you measured the amplitude from, right? The amplitude should have started with 0 being at its equilibrium position where it's hanging, not moving, not swinging. And you measured amplitude in terms of your distance away from equilibrium. Well, at equilibrium, what the definition literally meant way back in the day was, let's say we have a car, right? It meant that your applied force on the car is equal to the force of friction on the car, and the weight of the car pushing down onto the road is equal and opposite the normal force that the ground is applying at it. And if all of those forces are equal, then you have a net force of 0. And if you have a net force of 0, then you have absolutely no acceleration. Now, that doesn't mean you're not going anywhere. According to Newton's first law, that just meant that you're not changing your motion. So if you're moving, you stay moving at that speed and in that direction. If you're not moving, then you remain at rest. And that's what equilibrium means. So you have the exact same sort of situation here. Before you pulled that pendulum back in your pendulum lab, there were no forces acting on it. And at that position, there is no acceleration. That doesn't change even if the pendulum's moving. At that lowest possible position, gravity and tension cancel each other out. There are no net forces. There are no acceleration. But because you had some measurable kinetic energy, you still have a lot of velocity. And it is that momentum from that velocity, or that kinetic energy, that carries you through and keeps that motion moving, keeps the whole pendulum in this state of periodic motion where it repeats itself again and again and again. And as you continued up to the other side, right, we can take these exact same boxes and describe them up over here When you get all the way up to that top where your potential energy is at its largest amount, you go back to having a maximum amount of potential energy and a maximum amount of gravitational forces acting on you, or tension forces. Really, it's the net force between the two. That was from the reading notes. But you will also have your largest value of acceleration, and your velocity up there at the top goes back to being 0 because your kinetic energy was 0. You come to a stop because you're being slowed down, negative acceleration. You turn around and you have a positive, large positive acceleration. And that continues all the way through to the bottom. So that's what's going on there. We're going to turn around and compare this directly to this spring. Because this line right here, if I highlight it for you, this line right here is equilibrium. And if we pull this little wooden block to the right away from equilibrium and leave it here for a fraction of a second, right before we let it go, there is a lot of elastic force pulling back on it, just like there was in the last example. And the moment you let go of it, that will have its largest value of acceleration. But when you let go of it, its velocity still starts at 0, just like my daughter on a swing. And as it moves from that far right position through equilibrium, when it's at equilibrium, there is no more force acting on it. The spring is satisfied. That is the spring's natural shape, which means there's no more acceleration. But it does have momentum. And that is where it's moving its fastest, just like the middle part of a pendulum swinging back and forth. And then the opposite is true. When you continue moving on to the left, past equilibrium, right? You keep moving to the left. You're compressing that spring. The more you compress that spring, the more force you're applying, the larger your acceleration will be, either a negative acceleration, slowing it down, bringing it to a stop, or as it turns around, a positive acceleration as it begins moving the other way. Either way, at that farthest left point, your velocity gets back to 0. This is the same sort of motion that a pendulum undergoes. And this is what Robert Hooke got credit for. The relationship between this that he was able to find was F equals negative kx. If you want to write this out in words, that's a really good study tip, right? Basically, it states the spring force on an object is directly proportional to the spring constant, which is the letter K. It's like the stiffness of the spring. All springs are made differently, right? The spring inside of a clicky pen is a little bit stronger than a slinky, and both of those are dramatically weaker than the springs that might be in the shocks of your car. And so every spring is going to be made a little bit differently. Either you'll be given the spring constant or you'll be given everything you need to solve for it. Really, it's just a rating of how stiff the spring itself actually is. So it's directly proportional to the spring constant and the object's displacement from equilibrium. And that was the letter X. So again, if you are looking at equations on your equation card or on the cover page, or doing a homework problem, or a homework assignment, and you're lost, you're confused, you don't know what these equations mean, go back to the book and write them out in words a couple of times, right? It used to be a punishment in detention way back in the day where the teacher would make you write things repeatedly. You know, I will not throw things in class or whatever 1,000 times so that it like gets ingrained in your memory. While we don't do that anymore, there was some validity there. Rewriting things multiple times is one of the best ways to commit them to memory. So if rewriting these equations out in words is the best way to remind yourself what each of these variables and symbols represent, it is a fantastic way to study. Trust me. Why do we need to include that negative sign? It's because this force is what we would call a restoring force. And what that means is if you go back up, I'm going to change my highlighter color. If you go back up and check out the direction that your elastic force and your displacement are in all of these scenarios, all of these situations, you'll notice they're opposites of one another. They're exact opposites of one another. Your displacement is always going to provide a force that is in the opposite direction of that displacement, because the spring, the rubber band, the pendulum wants to go back the way that it was. It wants to get back to equilibrium. So force and displacement are always opposites. So let's do a practice problem. We're going to do a couple of them, and then, this video should be nice and short. If we've got a mass of 0.55 kilograms hung on the end of this vertically hanging spring right there, it's going to cause it from equilibrium, that's what this represents, that's equilibrium, to be to be stretched from equilibrium down to this new position. That new position represents a negative 0.02 meter displacement. All right, that's centimeters, so we divide by 100 because centi means 100. It's a century, 100 years. So it's 1/100th of a meter. And we're looking for K. Now, normally I would already know what the units for K are, but this is our first worksheet, so we're going to figure out what those are from the equation itself. Now, the only equation we've talked about so far is Hooke's law, which is F equals negative Kx. It's the only equation you should be thinking to yourself, I need to use this equation. We don't have a force. We do have a mass. That mass on the end of the spring is causing it to fall in a downward direction, moving in the direction that the force of gravity is going to make it move. And so technically, because I gave you a mass, you can't use that value directly, but you do have everything you need to figure out what force is causing this object to move. So that force is 0.55 kilograms, the object's mass, multiplied by gravity, which is negative 10 meters per second squared, and we're going to get negative 5.5 newtons is the weight of this object. That is the downward force. Now, the spring isn't pulling the mass downward. Gravity is pulling the mass downward, and let me erase this real quick. Gravity is pulling the mass downward, and the spring is pulling the mass back up, trying to counteract that. So the force the spring exerts is a positive 5.5 newtons. Right? That's a nuanced detail, not the end of the world. For this unit, I'm just looking to make sure that you keep force and displacement vectors to have opposite signs when you go to plug this in. So I'm not going to be a stickler over whether or not your answer is positive or negative, so long as when you set it up, one is opposite the other. That's all I care about. So we get a positive 5.5 newtons is equal to negative K multiplied by negative 0.02 meters. This is why we divide both sides by your distance, because K multiplied by that distance, you have to divide to undo it. And you're going to get a positive because your negatives cancel out. 275, your units are a Newton per meter. Literally every meter you pull this spring or compress this spring, it requires 275 newtons of force to do that. Right? If you wanted to do 2 meters, then it's like, what is that, 550 newtons. To get it to move 2 meters. That would be what the spring constant really does for you. 5 conceptually definitely going to be on the exam. I won't ask you something like number 6, but here's the main idea. Most of us are good with this. The more mass you have on the end of that spring, the more weight it will have, the more force the spring has to apply in order to get it to stop moving, which, because these were, key word, directly proportional, because they're directly proportional to one another, it's going to increase your displacement. That's it. Next page, 7, 8, and 9 are all going to use Hooke's law, right? Number 9 is a little bit more like what I just did in number 4 with you guys, where you have to find the weight of the mass on the end of the spring. Oh, no, you're looking for the spring constant. Never mind then. One of these I thought you had to find the mass. I guess not. Don't worry about it. So these will all be pretty straightforward. Simpler than what I just did. I guess that's my point. Number 10, be careful with. I give you a spring constant, K. I give you a distance, which you should convert to meters, 0.165 meters. Should be what you use in your equation, but then I ask you for potential energy. That's new. There's only one equation for potential energy in this unit. We're talking about springs, not gravity. So we're not using mass multiplied by gravity multiplied by height anymore. So this equation is 1/2 kx squared. Square your displacement, multiply by k, and divide by 2. That's all that one really needs to be. Number 11 is the same equation, working backwards. Last couple things we talked about in class were really the period of pendulum equations. So if we're looking for period of a pendulum, the lab even gives you this equation. The equation for the period of a pendulum is 2 pi L over G. Now, L and G are both under that radical. So if I give you the length of the pendulum and ask you to solve for period, for the most part, this first one's pretty straightforward. It's going to be your 1.5 meter distance divided by gravity on Earth is 10. And we're going to continue to use 10. On the lab, I do expect you to use 9.8 because labs, we need to attend to a little bit more precision. But for homework, for exams, 10 is good enough for me, right? It's good enough for the AP exam. It's good enough for me. So, plug that in. Make sure you can get the same value. I do not encourage you for this next one. I ask you, how long is the pendulum? So you're solving for length. I give you the period of 2.5 seconds, and then I give you a value of gravity on the moon of 1.6 meters per second squared. That's great. Do not, please, under any circumstances, ever use this equation. I'm going to put it in red to solve this. Not that you can't do it. I believe in you. I believe you can do this, right? You're going to swap out T for 2.5. You're going to swap out G for 1.6, and then you're going to try and solve for L. And inevitably, 9 out of 10 of us are going to mess up the algebra trying to do this on the exam, because on the exam you're moving faster than you normally would on homework, and we tend to make silly, small, little mistakes. But the algebra here is going to take a second. Now, your Algebra 1 class freshman year, yeah, you should have the skills to do it. But I don't encourage you to, because there's a lot of room for error. So, I'm going to give you two equations for 14 and 15, and these are the two that I would like you to use. If you're asked to solve for period, use the equation that's on the cover page. If you're asked to solve for the length of the pendulum, the equation I want you to use is L equals T squared multiplied by G divided by 2 pi squared. Keep 2 pi in parentheses. That's the equation I want you to use. It's already rearranged for you. This isn't like F equals ma, Newton's second law, where if I ask you to solve for acceleration, I believe in you. You can solve for acceleration, divide both sides by m, and you're done. This equation for a period of a pendulum is way more complicated. So please, 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 please use these rearranged versions. Have these rearranged versions on your equation card now. Those are the ones that I want you to use when asked to solve for acceleration due to gravity. This is actually number 4 on the lab as well. There's the answer to it. You're welcome. These are the ones that I would like you to use. Double check. Please don't be one of those folks who just writes down random gibberish and then copies my answer from the answer key trying to get points on the homework. That's not going to serve you well in the exam. We've noticed that lately for like the 15 or 20 of us who still do that. Give them a shot. Plug them in. See if you can get the answers I have at the bottom of the page. If you can't, let me know. That way I can help you. But that was what we did in class. If you have any questions or concerns, please don't hesitate to ask.